Yes. Any question? So the topic, whatever I will be teaching now for next 2-3 days, that is complex reactions and its kinetics. So under complex reactions, you will have 3 different type of reactions. One is chain reactions or chain reaction. So under chain reaction, we will see the HBr formation. Several reaction we can write which comes under the category chain reaction. Mostly free radical reactions, those are following the chain reaction mechanism. So next I can say consecutive reaction. Consecutive reaction. So consecutive reaction, by the word you have understood. In the consecutive reaction, first initially the starting material will give some intermediate B, and B will be later converted into the final product C. So there will be, I can show more number of steps, but for uh, sake of simplicity, I can show only 2 steps in consecutive reaction, A to B and B to C. So C is the final product, B is the intermediate product. So, but B is unstable, that converts into C. So you have to follow the kinetics of this reaction. And third type is parallel reaction. Okay, so uh, uh, parallel reaction, that one you have seen regarding other name also, competing reaction. So parallel reaction or competing reaction or competing reaction, where more than 2 or, okay, so I should erase the board also, something was written here. So in competing reaction, what I can say, that the starting material A can follow 2 reaction path. A can go to the product C, A can go to the product D. That means 2 reactions simultaneously is going on. More than 2 reactions also can be going on. So I can show only 2 reactions, that is A to C and A to D. So this type of reaction or kinetics we can follow, that is known as parallel reaction or competing reaction. Okay. So examples in organic chemistry, you know, so many reactions, those are parallel reaction. So in that case, like if you do the organic reaction, more than one product you may get. So those are example of parallel reaction, like ortho substitution, para substitution, or ortho para together you will get. So, so those kind of reactions are comes under those reactions comes under uh, parallel reaction. Okay, so chain reaction I will start after completing consecutive and parallel. Okay, so HBr formation, I will give example and you can see how chain reaction are taking place. Okay, so first I will start today consecutive reaction. What is consecutive reaction? So taking a general example, and I will derive the rate equation, and from rate equation ultimately we will calculate the concentration of the final product. That will be our aim, final product, or we can write the concentration of the starting material after some time. Okay, so first I will start consecutive reaction, then I will come into parallel reaction, and finally chain reaction. So in consecutive reaction, I have written A to B, B to C. Now I can assign two rate constant K1, small k1, small k2. Okay. So now the thing is, you have to assume one thing for sake of simplicity. You can consider this reaction rate can be uh, it is like depend on the reaction. Uh, Reaction can be more than first order, but for sake of simplicity, we will consider the reactions A to B and B to C all are first order reaction. So we have to consider these are first order reaction. So that overall equation will look simple. So there are two steps, A to B and B to C, both are first order with respect to the reactant. Okay. So if you start the initial concentration of A, initial concentration of A is C0. So at some time, what you will see at time t, what you will see A will be converted into B and B will be converted into C. But since rate constants are not same, K1 and K2, they are not same. K1 may be greater than K2 or K2 may be greater than K1. So what will happen at some time t, there will be a mixture of A, B and C in your product mixture. Okay, A will not be completely converted into B and B will not be completely converted into C. You will have a mixture of all the component. So starting material also will be there, because you know in first order reaction never completes. So A also, unreacted A also will be there. Some amount of B also will be there, and some product also, C product also will form. Okay, so at some time C, you will see the total component C naught. So C naught, you can write mole per liter or whatever concentration scale you can write. So this is the initial concentration C naught. So C naught will be summation of C1, C2, C3. So what is C1? Let's say C1 is concentration of A. What is C2? C2 is concentration of B. And what is C3? Concentration of component C. Okay, so because you know whatever mass is taken, that mass only will be there in your reaction mixture. So mass will not be generated during reaction. So total mass due to conservation, it will remain same. So total C naught will be distributed into unreacted C1, then some amount of C2 and final product C3. Okay. Now I can say the reaction you can write in terms of different component. You can say the component A. So if you see the reaction A, it is disappearing. So the disappearing of A, I can write minus dA dt. So that is negative because A is consumed. Similarly, you can have B component also. The B component I can write as, because B, if you see the reaction, B is produced in the first step and B is consumed in the second step. So I can say B is forming in the sense at some particular time, that is not at time infinity, some amount of B is present. Okay, so I can say component B is forming dB dt. I have put positive sign because B is forming in the reaction mixture. Initially at time t0 there was no B, but after some time B has formed, so that's why I have kept positive sign. Now you can write C. So C is also forming dC dt. So if you want to write rate of change in concentration of A with respect to time dA dt, I can write according to rate equation K1 into at that time concentration of A is A. So I have considered the reaction is first order, so power is 1. So B is concentration with respect to time. It will depend on two steps. First step it is forming, second step it is consuming. So first step it is forming, so I can say its concentration change, it will be written by K1 into A minus K2 into B, I can write. So this is the formation step, K1 into A, that is the rate uh, of the formation, and the disappearance of B is minus K2 into B. And in case of C, the formation of C, it will depend on the second reaction, K2 into B. So is it fine to you? So this is the first step is the disappearance of A. So that's why minus sign. Second step B is forming. So B is forming by so its concentration is changing into two reaction steps. First step is formation. Second step is consumption. So it is change of concentration of B will be related by two uh, component, and third is formation of C. Now I will be focusing on step by step. I will be showing how concentration of A will be changing, how concentration B will be changing, and finally how concentration C you can get it. So let me write with respect to A. So I already told that concentration of A, that I can write the concentration of A I have written in terms of C1. So I can write at particular time it is dC1 dt K1 C1. Okay. Now this is a first order reaction. So first order reaction, do you remember what will be the final concentration C1? It will be C naught e to the power minus K1 into T. So this is the general form. The derivations are there in your book PDF, or you can see your school book. So any component, it is following the first order rate. Then at particular time T, its unreacted component will be C1. It will be related to the initial concentration C naught multiplied by e to the power minus K1 into T. So this is the concentration of A at some time T. Okay. So C0 is the initial concentration. Now I can get the concentration of B. So this one I will just erase. So I can say, so each component you should know at particular time how much it will remain. Okay, so the concentration C1, what I already told, that one you will see it will be related to the initial concentration by this form. C1 will be equal to C naught e to the power minus KT. Now my next step is B, calculation of concentration of B. So I already told dB dt, you can write K1 into C1 and minus K2 into C2. Okay, so C1 is the concentration of A and C2 is the concentration of B at particular time. Now I should write in place of B, I can write it is as C2. Okay. Now you can see C1 is, I can substitute K1 C0 e to the power minus K1T K2 C2. So this differential equation you have to solve. So this one have you done before? Anytime? So one thing you can do, you have to multiplying with e to the power K2T on both the sides. So what I will get? I will get dC2 dt. So this is a trick. So you have to remember Q1 C0 e to the power minus Q1 plus K2 to T minus K2 C2 e to the power K2 T. Okay. So I should change the side. So I have to rearrange dCt dt dC2 dt e to the power K2T plus K2 C2 e to the power K2T. If I do some mistake, please inform me. Minus, I can write it is as K2 minus K1T. So if you integrate on both the side, what you will get? So I have, so you can see after integration, I have come at the bottom of the page, integration. So left hand side you can see it is a form C2, it is a product of two term C2 into e to the power K2T. So you can see, so it is a product, so one will be kept constant, one will be, so reverse you can think with respect to time I am writing, and in the right hand side you can write as K1 C0, you have to divide with the constant K2 minus K1, you will have e to the power K2 minus K1 T and an additional constant Z. Now I have to find out what is Z. Fine. So I will erase the upper part. So C2 you have solved. Now you can see C2 is only the variable here, and another variable, that is time, that will be always there. But C2 unknown, I can get it with respect to time if I know C0. So Z also have to calculate. So I can erase. I'm going little slower because this is a derivation, so you can practice. So when time equal to 0, C2 will be also 0. When there is initial, when you are starting the reaction, that time there was no component B, that is why C2 equal to 0. So applying this condition, you can get the final unknown constant Z. Okay, and by putting the value of Z, you can get the final form of C2. So if you see the final form, if you put C2 equal to 0, then you will get the, when T equal to 0, C2 also 0, you will get Z equal to, what you will get? Z equal to minus K1 C naught by K2 minus K1. Okay. Now if I substitute the Z value in the equation, then I will, and after rearrangement, I will get final form. C2 will be equal to K1 C naught K2 minus K1 and e to the power minus K1T minus e to the power minus K2T. So this one you can see, and you can derive also after putting the value of Z, and you have to rearrange, and you will finally get the concentration of component B, that is C2. So I have two component now, component A, component B. After time T, what will be its concentration, that is C1 and C2 respectively. Now I have to get the C3 value. C3 is the concentration of product. Okay, that means it will be, you can get it from the initial equation. I told C3 will be C0 minus C1 plus C2. Now you can substitute the value of C1 and C2. So C1 I already told, C1 will be equal to C2 into C0 into e to the power minus K1T, and C2 you can see this form. So you have to substitute both, and finally you will get a concentration of product. Product is your C3. C2 is a intermediate, so its intermediate concentration also not equal to 0. So you will also get some value. Final concentration will be 1 minus K2 by K2 minus K1 e to the power minus K1T minus K1 by K1 minus K2 e to the power minus K2T. Okay. So you have now three component at some intermediate time. The unreacted component 1, that is C naught into e to the power minus K1T. The intermediate, its concentration will be C2. It will be given by this big equation. And the third one, that is the final product, that's concentration is C3. That will be given by this equation. So you have understood what are the three components. Now I can approximate. Any question? So
No,
this
sir.
derivation, okay, so this derivation you have to practice. So now I'm approximating that K1 and K2, that is the rate constant for the formation of B and disappearance of B. Now if I say, if K1, so I can erase this part, I can make some graphical interpretation that is important. So let's say the rate constant K1 is larger than, much larger than K2. K1 is much larger than K2. So what will be the situation? B will form or B will consume immediately?
We will consume immediately.
No, K1 is the formation of B. So in the reaction
So
mixture,
it
you will,
will be consumed immediately.
so if K2 is larger, then B will be consumed immediately. So if K1 is much larger than K2, then the concentration of C2, that is the concentration of B, I can see it will be
Constant.
constant. I should not say, because there are two reactions. One is formation of B, another is consumption of B. So when B has rate constant of formation of B is much larger than rate constant of consumption of B, then concentration of B will rise. Okay, so it will accumulate in the reaction medium. Okay, so that rate constant, that concentration, I can get it from this final form of, so you can see C2 and C3, these two equations are important. Now if I consider C3, when K1, so I can change the color. So when rate constant K1 is much larger than K2, then the, which one is larger? K1 is larger, so e to the power minus K1, it is very high, so negative K1, that means this overall product will be very small.
Zero.
So I can,
Negative.
e to the power minus infinity, so it in minus infinity is almost 0. So I can ignore this term. So that in that case, concentration, final concentration of C3, it will be 1 minus, and if you see in the right hand term also,
Okay.
so it will be almost 1. You can consider K1 is much larger than K2, then K1, I can ignore the K2 with respect to K1, so K1 by K1, it is equal to 1. So my rate constant will be, final concentration term will be e to the power minus K2 by T, when K1 is much larger than K2. Okay, so when K1 is much larger than K2, then this term will be, you have to ignore, then final form will be this one. Now another term, when I can approximate, when K2 is much larger than K1. So when K2 is much larger than K1, then what will happen? It will be reverse. In the reaction mixture, B will not be formed, it will be consumed immediately. So I can change the color and I can write it. So I can say in other way, it will be to the power minus K1 into T, when K2 is much larger than K1. So this is the final concentration. You can approximate to this one. Okay. So C2 also accordingly you can get it. Now the major part, or major important, or most important thing, you have to plot. Okay. So how you can represent all the three component report, presented in a same graph. Okay, with respect to time. So first case, so concentration versus T. So component A, that will be constantly decreasing with time. So first order reaction. And now what will be the concentration of C? C will be constantly rising, exponentially it is rising, and then after some time it will get saturated. And concentration of B, that is important. So concentration of, so this is component C, and component B, that is important. How its concentration is changing, because you can have two different condition where either K1 is much larger or K2 is much larger. So when K1 is equal to K2, then concentration of B will be like that. So this is the condition when K1 approximately equal to K2. So at some time concentration of B will rise, and after that B will fall, because the rate at which B is forming, it is equal to the same rate it is consumed. So I will have some formation of B at some intermediate time, then it is rapidly falling, following first order rate equation. And then in the second case, the rate constant K1 is much larger than K2. Then what will happen? So first I can write for A will be always rapidly falling and then getting saturated. It is like a first order rate equation, rate following rate equation. And then concentration of C, it will also rise exponentially, then it will get constant. So it is C, this is component A, and B, I told K1 is much larger than K2. That means B will form a lot and then it will fall. You have understood why it is so? Because K1 is much larger than K2. Okay. B will form and then it will, following first order rate equation, its concentration will fall down. And in the third case, when K2 is much larger than K1, in that case I can plot the third graph. Concentration against time, the condition is K1 is much smaller than K2. So B will be consumed more. Whatever B will form, immediately it will be converted into product, because rate constant for B2 consumption is, B consumption is more. Okay, so this is the concentration of A. C will rapidly rise, because whatever A is formed, that will be immediately whatever B is formed, that is rapidly converted into C. So concentration of C, it will steadily rise. Okay, and concentration of B, that will not get any time to be accumulated. So concentration of B will be always small in the reaction mixture. Okay, so concentration of B always will be small when K2 is much larger than K1. So B will never accumulate in the reaction mixture. It will, whatever it will form, it will be immediately converted into product C. That's why concentration of C, it will always be very high in the reaction mixture. And this curve, it should always follow the relation C naught equal to C1 plus C2 plus C3. So at any time, so my graph maybe not well in the scale, but at any time, if you take, let's say the time is here at this point. So at this point the concentration of A plus concentration of C, so this is the concentration of A, this is the concentration of B, and that is the concentration of, so this is the concentration of C, this is the concentration of A, and this is the concentration of B. So this is these are the three height. If you sum it up, you will get the initial concentration, that is C naught. So if I take this point, at this point concentration of A, this height, then the second height is for C, and the third height, that is, or third length, that is the concentration of B. If you sum it up, you should get the value of C naught. Okay. So at any time for any graph, this condition always should hold, that C naught will be summation of C1, C2, C3. Summation of their concentration should be the concentration initially, C naught. Okay. So now my question to you, that anytime C, the concentration of C, product C, will it reach C naught? C can reach to C naught. C naught is the initial concentration of A. That means in the reaction mixture, you will not have any A, you will not have any B, completely C. Will it be possible?
Yes, sir.
Yes or no?
Yes, sir.
Why?
क्योंकि रिएक्शन हमेशा चलते रहेगा, स्टैटिक थोड़ी है ये.
Because this is a first order reaction. So
Yes.
in first order reaction, A and B, I have considered both are first order. That's why they will never be 100% consumed. Okay, so if you remember the graph, the concentration of A, it will never touch 0. It will be always parallel to the time axis. It will be very, very small, but it will still be, it will not still go to 0. Okay, so that means C cannot be C naught. So it can be C naught when time is infinity. At infinite time, I can consider that A and B both have consumed 100%. Okay, now the next point is, what will be the maximum concentration of B you can get? Okay, so that is another important derivation. I told that B will be reaching maximum and then it will fall. In one case, B will be, K1 is much larger than K2, then B will be accumulated a lot and then it will fall. And in another case, B will not be accumulated much, it will rapidly fall or rapidly converted into C. So let's say I am considering the case 2 where B will be consumed a lot, not consumed, it will be formed a lot at the intermediate time. Okay, so in the second graph. So now my question is, what will be the amount, maximum amount of B? Okay, and what will be the time, what will be the T max when B will be maximum? So that is like a, I think the principle. So I can use the principle of steady state. Have you know the principle of steady state? Do you know? So I can come to the equation straight away. So this is the condition. So I already told concentration of So this derivation I will show and then I will stop here. So A is converted into B and B into C at time t. You will have A will be equal to C1 concentration of A, concentration of B will be C2 and concentration of C will be C3. And now my question is C2, that is the concentration of B, that one I have told that it is K1 into K1 into C naught, K2 minus K1 e to the power minus K1 T minus e to the power minus K2 T. So this is the concentration. So the maximum B, that is the maximum concentration of B max, B, that is the B max, I can say. So I can write the same thing, just I will write, I can erase the graph. And I can say when B is maximum, I can say time is maximum. So that is the maximum time. First I have to get what is T max, the time at which B is maximum. So that time is T max. First I will get the T max, then I will put the value of T max to get the B max. Okay. So at when B is maximum, when B is maximum, I can say concentration of dB dt equal to 0. So this is the concept steady state approximation. What is meant by dB dt 0? It means A is converted into B, B is converted into C. So there will be some at particular time when the rate at which B is forming and the rate at which C is forming or B is consumed. So the rate at which B is formed and the rate at which B is consumed, both are equal. Then I will have maximum amount of B. Any question? Do you have anyone is who is
Like concept.
so when B is maximum, then I can say the rate at which B is forming is equal to the rate at which B is consuming, both are same, then only B will be reaching maximum amount. So its concentration with respect to time will not change. So B is forming and B is converting into C. So this B, its concentration is rising and concentration of B is consumed by forming C. Okay, so when their rate is equal, I can have maximum amount of B form. So in that, at that particular time, I can say its concentration is not changing, it is constant, and I can say first order or first derivative of concentration of B with respect to time is equal to 0 because it has reached to the maxima. So you know at maxima first derivative is equal to 0. So this is the concept in steady state. Okay. So you know already I told that concentration of B, it is related to, it is equated to k1 into c naught by k2 minus k1 into e to the power minus k1t minus e to the power minus k2t. So I have to do the first derivative with respect to time. So I have to differentiate this equation with respect to time. So differentiating with respect to time and equating to 0, and we have to get the value of t. So first derivative, if I make it, so that one easily you can get it. So dct dc2 dt, that one you will get it. So mine, I am writing from the book straight away, you can derive. So you will get the same form also. I am not, time is less, so I am writing straight away. K1 C naught minus K1 C naught, K2 minus K1, you will have K1 e to the power minus K1t minus K2 e to the power minus K2t, if you do the first derivative. And what I told, you have to equate to 0. Okay, so this equation will be equal to 0. And I told this, when there will be equal to 0, I can say there t max, this first derivative is equal to 0 when time is maximum time. Maximum time means b is from maximum, that's why I told time is maximum. Now from the equation you have to rearrange. Now you can see it is equal to 0, so it can be 0, but you know k1 not equal to 0, this k1 is not equal to 0, c naught, that is not equal to 0, so this is also not equal to 0. So this equation can be 0 when the term inside the bracket, that is 0. So I can say the equation can be 0 when the quantity present inside the bracket, that is equal to 0. That means k1 e to the power minus k1 tm, k2 e to the power minus k2 tm equal to 0. So according to steady state principle, the first derivative is equal to 0. So this overall term is 0, but k1 is not equal to 0, c naught is not equal to 0. That means the term what is present inside the bracket, that must be 0. So now you have to rearrange and you will get tm will be equal to, very easily you can get it, it will be ln, this derivation you should practice, ln k2 minus ln k1 k2 minus k1. So it can be asked in the exam or as a assignment. So the time at which concentration of B will be maximum, that you can get it by this equation. And what will be the maximum concentration of B? That is B max, that you can say as I already told, that is C2 max. C2 is the concentration of B component, and if you put that one in the equation, the value of Tm in the equation, you will get, it will be C naught. This one also you have to calculate. You can try in your home this derivation, K2 by K1 minus K2. Okay, so this condition, so this condition is for deriving when k1 is much larger than k2. Okay, so this was the initial consideration we have to make, that k1 is much larger than k2, then b will rise and it will reach a maximum amount. and that amount will be given by C naught into K1 by K2 to the power K2 by K1 minus K2. So these two derivation you should practice. One is the time at which concentration of B will be maximum, and second is the amount of B when it will be maximum, means what will be the maximum amount. So these two form you should practice. Okay, so I will complete today's lecture. I will stop here. So
Thank you.
so few things you have learned today. One is when consecutive reactions are going on, so so none of the component will be zero at some particular time. All will have some amount present in the reaction mixture. So A, it will be the starting material, its concentration is C1. I already told C1, its concentration you can calculate by the first order equation. Then comes B, intermediate, its concentration is C2, and final product, that is C3. So C1, C2, C3, all independent concentration you have to calculate, and you have to see the graphical representation, how K1 and K2, that is the rate constant for the first step, and the second step, how they will govern the overall concentration of intermediate B, and that B, it is given by its form. And finally you can see what will be the time when the maximum amount of B you can get. That T max is given by ln K2 minus ln K1 by K2 minus K1, and B max will be this one, this final form, and this form you can get it when you approximate rate constant of formation of B is much larger than rate constant of consumption of B. So you can simplify into this form, C naught into K1 by K2 to the power K2 by K1 minus K2. Okay, so in the PDF you can get it C1, C2, C3, but these two final form T max and B max you should derive. I have shown the way how you can derive. Final form you should get it. Okay, so I'll take the attendance and I'll stop today's lecture. I think most of you have left, or no, still you are there.
No, sir.
Okay, now you are there. Something is showing here. Okay, so I'll stop here. If you have any question, you can ask. Otherwise, we will meet next week, next Monday, with the parallel reaction. Okay. If you have any question, do you have?
Yes, sir. One question I have.
Please ask.
Sir, not in this. Sir, actually, the effect of temperature on rate of reaction. Sir, actually, that part is not clear.
Okay, so then next class I will start from the Arrhenius equation itself with the collision theory. Okay, so it will take 5 to 10 minutes.
Yes, sir. Yes.
So please remind me next class, when I will start the second step.
Okay, sir.
Okay,
Thank you,
so
sir.
I'll, okay, welcome. Already 10 o'clock, that's why I'll discuss in the next class. Okay, so see you on next Monday. Okay, bye.